Okay, so we continue to discuss the conditional distribution for the absolute continuous case. So the next proposition is an application of the previous proposition. So if x and y are two jointly absolutely continuous random variables with a joint PDF f of xy, then for any Borel set A in R, we have that. So this is the this is an event described by random variable x. So the probability of this event can be computed by this integral over the whole real line, and the integrand will be the conditional probability of the event that random variable x is in the Borel set A, given that random variable y has a specific value equal to y, okay, and weighted by a PDF of random variable y, okay. And so the proof is by application of proposition 6.5.b with the Borel set B to BR. So we have that P probability of x in A, which is equal to the probability of x in A, and y is in R. Okay, so y in R is just the total event, the sum of spaces. Okay, and so that this is actually equal to okay. So this is from proposition 6.5.b. Okay, so here we use that, and so this is our result. Okay, so this proposition is quite easy to see. Now, now we provide a condition of independence between two jointly absolutely continuous random variables. Okay. So two jointly absolute continuous random variables, x and y, with a joint PDF f of xy, okay, are independent. If and only if the conditional PDF of random variable x given random variable y with a specific value little y, okay, is equal to the unconditional PDF of random variable x for almost all point xy in R square. Okay, where the marginal PDF of random variable x can be computed from the joint PDF, okay, by this integration. And again, the marginal PDF of random variable y can be obtained by the joint PDF, but integrate over all x in the real line. Okay. All right, so the proof. Okay, we see that this identity for almost all points, that's y in R square, it is a necessary condition. Okay. So now we use a proposition in section 6.2, since x and y are independent. Okay. So we know that f of xy, okay, so the joint PDF is equal to the product of their marginal PDFs, okay, computed in this way, right? All right, so this equality is good for almost all point xy in R square. Okay. All right, so this result is by proposition. By proposition 6.2.c. Okay. Okay, and so we let A to be the point, okay? So it lets A to be the point in the real plane such that f of xy not equal to the product. Okay? Not equal to product. Right? So it's clear that the area of A is 0. Okay? The area is 0 because that we say that the equality holds for almost all xy. Right, so the meaning is that this is set for all points. We collect all points such that the equality does not hold. Okay? Has area which is 0. Okay, so that. Any questions about that? This is just the meaning of almost all. Okay. All right, and so we consider a point xy, okay, in R square, but not in A. Okay? Suppose we consider a point that not in A. All right, so if the marginal PDF of random variable y is positive at little y here, okay, so we have, by definition, we know this is this ratio, right? By definition. But because the point is selected for all the points, not in A. So if it's not in A, which means that the identity holds. Okay, so we can have and we can cancel them. Right? So we establish the identity, okay, for this case. Okay. Now if this is 0, now we have that equal to the unconditional PDF by definition. Okay. Okay, by definition, yeah. Okay, so we prove whenever a point, right? So we conclude that the conditional PDF of random variable x given random variable capital Y has value little y is equal to the unconditional PDF for all the points in R squared minus A. Okay? Which means that the identity is good for almost all points, for almost all xy in R squared. Okay, so we proved that it is a necessary condition. Any questions about the forward part? Right, so if no question, then we will prove the backward part. Now, from proposition 6.5.8, we have that the joint PDF f of xy is equal to the conditional PDF of random variable x given random variable y has value y times the marginal PDF of y. Okay? And this equality holds for almost all xy in R squared. All right, so we let B to be the set of all points in the real plane such that the above equality does not hold. So we say that okay? All right, and so it is clear that, again, the area of B is 0 again. Okay, so it's 0. Okay? Now, we have this condition, right? Because we want to show this is sufficient. So we let, so that this is A, right? to be the point. Okay, we have already shown here, right? Oh, no, C. So let's see. With a point such that not equal to, okay, right? And then by assumption, right, the area of C is 0,2. Okay, it's 0,2 because the equality holds. The equality holds for almost all points in the real plane. So if we collect all points in the real plane such that the identity does not hold, then the area of this set C is 0,2. Okay? All right, so now consider a point, all right, xy in R square, but without B union C, okay? Okay, so for a point in the real plane, which is not in B, nor in C, right? Neither in B nor in C. Then we have, because it is not in B, so that we have that so we have this identity, and we have this identity, okay? Is that okay up to now? Okay, and so this implies that because this one is equal to this, so this implies that the joint PDF is just the product of these two marginal PDFs. Okay, so we conclude that fxy equal to fxy for all the points in R square minus B union C. Okay? Now, the area, so now the area of B union C is less than or equal to the sum of the area of B and the area of C. Is that clear? Okay, and so this implies that the area of B union C is 0, 2. Why? Because the area of B is 0, the area of C is also 0. So their union has area 0, 2. Okay, and because the area is 0, so that the identity, all right, this for almost all point xy in R square. Okay. Right. So this proof is a very good illustration to understand the meaning of concept for almost all, right? What is almost all? Okay. Any questions? Okay, so now we have discussed conditional distributions when we have two jointly absolutely continuous random variables with a joint PDF. Now we extend this result to a finite number of jointly absolutely okay, we consider two collections. One is so-called X collection, the other is called the Y collection of jointly absolute continuous random variables. So this m plus m, so we have m plus m random variables, and this m plus m random variables are jointly absolutely continuous with a joint PDF, okay? With a joint PDF with m plus m variables. So you can see we have n x variables and m y variables. All right, and it has been shown that the random variables in the X collection, so these n random variables are jointly absolute continuous, okay, with a joint PDF. Okay, so this joint PDF is denoted as here and can be computed from the joint PDF of n plus m random variables. Okay, so that this would be first integrate over d1, dy2, dym minus 1. So that is we use iterative integration. All right, so the integrand here is the joint PDF of the m plus m variables. Okay, so we started from integration over y sub m, all right, and then go integration over y sub m minus 1, etc. Okay, and so the final function will be a function of x1, x2 up to x7. Okay, so this is the joint PDF of x1, x2 up to xn. Okay? And y1, y2 up to ym are also jointly absolute continuous with a joint PDF, okay, which is y1, y2 up to ym, d to y1, d to y2 up to d to ym. All right, so now we integrate over the x variables. Okay, so of course we can do iterative integration. Okay, so now we have that. Okay, now with this information, so now we define conditional joint probability density function. Okay, so the conditional joint probability density function of the x variables. Okay, x variables. Given that the y variables has specific value. Okay, so we give this known data, all right? So we know the known data here is defined as the following. So the notation would be x variables given y variables. Okay, so you can regard that the conditional joint PDF is a function of m plus m variables. Okay, and it's defined to be here. Okay, and this is so. The first case is that the joint PDF of this m plus m random variables divided by the marginal joint PDF of the y variables. Okay, the y random variables. So this is the marginal joint PDFs. Okay. And so this is the case if the denominator is positive, okay? So if okay, it's positive, right? So when this marginal joint PDF of y random variables is equal to 0, then this conditional joint PDF becomes to the unconditional. So we define to be the unconditional one. Okay, if equal to 0. Okay, so for all x1, x2 up to xn, y1, y2 up to yn, ym in the m plus m dimensional Euclidean space. Okay, so the idea, just a generalization of the previous idea we discussed before. Even though the notation is a little bit cumbersome, you see that because we have m plus m random variables, a lot of random variables, so it just takes times to write down the expression. But the concept is the same. Okay, so let me know if you have any question. Okay, so of course that we know in the two random variable case that the definition of conditional joint PDF is useful, all right, to compute the probability of events described by X random variables, as well as by Y random variables. Okay, so specifically, all right. So, but before that, we use the conditional joint PDF to define conditional probability. So, for any Borel set, okay, U in the n-dimensional Euclidean space. Okay. And we know what is the Borel set in n-dimensional Euclidean space. Well, we use the n cells, right? We define n cells. And we can do complement, countably many complement, intersection, and union, this kind of set operations, and to form, to obtain any Borel set. So for any Borel sets U in R, we define the conditional probability of the event that the X random vector has a value in the n-dimensional Borel set U. Okay. All right. So the conditional probability of this event, given that the Y random variables have a specific value. Okay, have a specific value here. So the probability of in U, given that all right, is defined by definition. It's defined by using the conditional joint PDF of X random variables given Y random variables. Okay, and integrate over all the points in the n-dimensional Borel set U here. Okay, so okay, and of course you have to. We should do the unfold integration, right? This is the unfold integral. All right. So actually, this is a sequence of definitions. Okay, and in particular, okay, the conditional joint cumulative distribution function of the x random variables given that the y random variables have specific value. Okay. Is defined as here. So this is f of x1, x2, up to xn, y1, y2, up to yn, of x1, x2, up to xn, given y1, y2, up to ym. Okay. So the definition is that the corresponding Borel set would be, okay, so it's a specific n cell, okay, given okay, so here the corresponding Borel set U so U will be Cartesian product with x2 okay. So the Borel set we use is the n cell, okay, and in each dimension we use the semi-infinite interval from mass infinity up to xi here. Okay, so the event, as we know, is in okay, this event is actually equal to the event that okay. Okay, and over of these n cells, by the definition, the integration becomes to, so we will have x1, okay, x2, xn, f of given all right, so this n-fold integration can be evaluated by iterative integration in any order, okay, in any order. So this is the joint CDF, the conditional joint CDF, I'm sorry. The conditional joint CDF of x random variables given that the y random variables have specific values. Okay. Okay, so we now write down proposition 6.5.E. Okay. Like the proposition 6.5.A, because in proposition 6.5.A describe the relationship of the joint PDF of two jointly absolute continuous random variables, two, right? Just two random variables. So let's x1, x2 up to xn, and y1, y2 up to y sub m. Okay, B2 collections of jointly absolute continuous random variables with a joint PDF x1, x2 up to xn, and y1, y2 up to y sub m. Okay, so this is our condition. Then we have that for each point. All right, so maybe I say, then for each point, y1, y2 up to ym, in the m-dimensional Euclidean space, we have the joint PDF of the m plus m jointly absolute continuous random variables is equal to the product of the conditional joint PDF of the x random variables given the y random variables has a specific value times the marginal joint PDF of y random variables. Okay, for almost all point in Rn. Okay. Okay. All right, and remark proposition 6.5.E implies that the joint PDF of the n plus m random variables is equal to the conditional joint PDF of x variables given that the y variables has specific values, okay, times the marginal joint PDF of y variables. Okay, so the equality holds for almost all points x1, x2 up to xn, y1, y2, ym in the n plus m dimensional Euclidean space. Okay. Okay, so this is the part. And the next proposition is an extension of proposition 6.5.b. All right, so if x1, x2 up to xn, and y sub 1, y sub 2 up to y sub m, if are two collections of jointly absolute continuous random variables with a joint PDF f of x1, x2 up to xn, y1, y2 up to ym. Then for any two Borel sets A contains in, so the A is the n-dimensional Borel set, and B is the m-dimensional Borel set. We have that the probability that the x random vector has value in the n-dimensional Borel set A, and the y random vector has value in the m-dimensional Borel set B. Okay, so this joint probability is equal to equal to an integral. So it's an m-fold integral over the m-dimensional Borel set B of the conditional probability of the event that the x random vector has value in A, given that the y random variable have specific value weighted by the marginal PMF of the y random variables. Okay, so we have so this is so that the previous definition of conditional probability of this event given this data, right, can be used to evaluate the joint probability, okay, of these two events. So this is an event described by the x random variable. This is an arbitrary event described by the y random variables. Okay, so we have this, and again, the next proposition is just an application of the previous proposition. So if x1, x2 up to xn, and y1, y2 up to ym are two collections of m plus m jointly absolute continuous random variables with a joint PDF okay. Then for any n-dimensional Fourier set A in Rn, we have the x random vector has value in A, has probability which can be integrated. Okay, so okay, as we pointed before, that this is actually an indirect way, okay, to compute the probability of an event described by this n x random variables here. Okay, through some additional information of about y random variables. Okay. And the reason is, in many situations, it's quite easy to compute the conditional probability of this event given specific value of the y random variables from the conditional joint PDF, okay, of x value random variables given the y random variables. Okay, right, and the last one is about the independence between two collections of jointly absolute continuous random variables. Okay, so two jointly absolutely continuous collections of random variables with a joint PDF f of x1, x2, xn, y1, y2 up to ym are independent if and only if if that the conditional join PDF of X random variables given Y random variables is equal to the unconditional join PDF of X random variables for almost all points in the n plus m dimensional Euclidean space. Okay. So this is about another necessary sufficient condition for two collections of jointly absolute continuous random variables to be independent. Okay. So up to now, we considered two special cases. Either all the random values are discrete. This is a discrete case. The second case is that the involving random variables are jointly absolute continuous with a given joint PDF at hand. Okay, so that we have this one. Now, next one we will consider mixed type. One random variable is discrete. The other random values is absolute continuous. Okay, so this quite often to occur in applications. Okay. So now, we next consider a discrete random variables called n, and an absolutely continuous random variables x with a PDF f sub x. All right. So we will consider this situation. All right. And without loss of generality, okay, we assume that unchecked integer values, and okay, if we need it, so we will say that the discrete random variable has integer values. Okay. All right. So now for each n, okay, how do we define? So how do we define the conditional probability P of n equal to n of the event capital N equal n, given that the absolute continuous random variable x has a specific value x. Right? So how do we define? So what we want, so that the probability of the joint event. Okay, so this is an event described by the discrete random variable, and this is an event described by the absolute continuous random variable x. and A is just a Borel set in the real line. Okay, so what we want that we would like to have here. Okay, for any Borel set A in R. Okay, so we need to find a way to define this conditional probabilities. Okay, of so that this is a function of little n and little x, right? Little n and little x. Okay. We deal with this situation when both random variables are discrete before in the previous section. In this section, we give a proper definition, okay, for two random variables which are jointly absolutely continuous. But now, how do we deal with this when we have mixed types of random variables? Okay. Now we deal with a much simpler one for any. So if we reverse the row of x and n, okay, so for any Borel set A in R, we observe that the conditional probability of the event x in A, given the event n equal to little n, x. We know this from chapter 3, right? So we know that probability of x in A x equal to. So if the given event occur with positive probability, then we know that this is just equal to the joint probability, right, divided by if it's positive. But when this event occurs with zero probability, then we define this is equal to the unconditional probability. Okay. Right? So in particular, the conditional CDF of x given that the discrete random variable capital N is equal to little n is defined as, so we can use that to define to be this conditional probability. Okay? It's equal to this one. Okay, so here we have conditional CDF here. Okay. Oh, but I'm sorry, I forget that with here with the A is equal to. Okay, so we take the Fourier set to be this interval. Okay, so this is the conditional CDF of X here. All right, so now this gives us a hint. So we assume that for each n such that this event has probability that the probability that random variable n is equal to n is positive. Okay, there exists a non-negative and integrable function on R denoted as fx, okay, such that P of x in I and in N, it can be computed as okay, for any interval I in R. Okay, so we assume this situation that for each possible value, right, so that this probability is positive, all right, n little n. There exists a non-negative and an integrable function. Okay. All right, so this function would be a probability density function for the CDF, for this conditional CDF, okay, such that for every interval, okay, okay, this conditional probability can be evaluated by this non-negative and integrable function for any interval I. Okay, and in this case, we say that the random variable x, okay, is conditionally absolutely continuous. Okay, given the discrete random variable n. Okay, and this. Okay, so this non-negative and integrable functions, okay, will be called a conditional PDF of x, given that discrete random variable n is equal to d to n. Okay. All right. So for the mixed type of random variables, we assume this situation. Okay. We assume that random variable x is conditionally, absolutely continuous, given the discrete random variable n. Okay. And which means that we can find a conditional PDF of x given that n equal to d to n, and for each possible value d to n. Okay. And of course, the existence of such a PDF, a conditional PDF, depends on the conditional CDF, right? Depending on this function. Okay. Any questions? Okay, so we assume this is a case. Again, remark, as before, to verify that a function, right, is a conditional PDF of x given x equal n with the probability that this event is positive, right? So it is sufficient to check that the conditional CDF of random variable x, given that random variable n equal to d to n, is here. All right, so we just check that whether the conditional CDF of x given capital N equal d to n is this integral, okay, of the test, the function under test here, okay. Now, it is clear that if a random variable is conditionally absolute continuous, okay? So in this case, so if we know that that the x is conditionally absolute continuous given this random variable n, then we can define a function which is the sum of all conditional PDF of x given n equal to d to n, weighted by what? By the probability of this event. Okay? So if we define such a function, right, so this function is a PDF of x. Okay, so that x is absolutely continuous. Okay. So this condition is stronger than the condition that x is absolutely continuous. Okay? So a random variable x is conditionally absolutely continuous given a discrete random variable. If this is true, then that random variable x is also absolutely continuous. Why? Because we can find a PDF for it. Okay, so we have, and the checking is quite simple. Why? To check this, we see that okay, so that we integrate over okay, so this is okay. So we put the definition of this function here. Okay. And because everything is non-negative, so the integration operator and the summation operator can exchange each other, the order of okay. And this is probability. The A here. But this one is equal to the condition CDF. Okay? So we have times into n. Okay? But the conditional CDF, all right, by our definition is here, is the probability that x equal to x given n equal to n times probability n equal to n. Okay. And by the decomposition formula, this is actually equal to this one. Okay. In chapter 3, we have a decomposition formula. Okay. So this event condition on, or if you want me to do it, so this is the probability that x less than x and n equal to n. Okay? So the conditional probability times this probability is equal to the joint probability. Okay? This is from the definition of conditional probability. But this event is a partition of the total event. Okay? So this is actually the probability that X and the union Okay, so this is the probability that so that this okay, so you can see that the integration of this function gives us the CDF of X. Okay. So of course that this is indeed a PDF. Okay. Right. So the required condition is quite natural, right? We require that the random variable X is conditionally absolutely continuous, okay? Given that the discrete random variable has value, okay? So any questions up now? Okay, now we know that this is our defining the requirement to have a conditional PDF, right? Okay, and so this one, this equality. So once the conditional PDF satisfies this identity for every interval, okay, for every interval, so we mark if okay, it's a conditional PDF. Oh, by the way, first of all, for convenience, we define that to be the unconditional one, okay? Because we know the existence of the PDF of X, right? From the previous checking, we know that this is by this one. This function is a PDF of X. All right, so we define that this is equal to X. Okay. If for those n such that the probability of this event is equal to 0. Okay. So for every n, which is not a possible value of discrete random variable n, okay, then we define the conditional PDF of X given n equal to theta n is just the unconditional one. Okay, just for convenience. Okay. And so, and if it's a conditional PDF of X given that n equal to n, then for every then that this identity can be extended, because this identity will require only for interval I, right? But this can be extended to any Borel set A. Okay, for any Borel set A in R. Okay, now with this assumption here, we're now able to define. So now we define the conditional probability of the event random variable n equal to d to n, given that x equal to d to x as here. Defined here. Divided by if the denominator is positive, but if the PDF of x, right, obtained from this equation is 0, then we define this is to be just the probability, unconditional probability. Okay. Okay, so this is our definition now. So now we are able to define that the conditional probability of the event, this event is described by a discrete random variable n, right? Given that the absolute continuous random variable x has a specific value little x here. Okay, so we have that. Okay, so the appearance of the numerator here, you can see is this part is the conditional PDF, okay, of random variable x given discrete random variable n times the probability. Okay, so this is actually the PMF, right? Okay, this is the PMF. So the numerator involving PDF as well as PMF. Okay, and the denominator is the PDF of random variable x. Okay, so this is our definition of that one. Okay, and so we know that this definition. So we are able to give such a definition because we make an assumption here. Okay, we assume the random variable x is conditionally absolutely continuous given discrete random variable n, okay? Which means that there exist non-negative and integrable function for each little n, right? With probability, right, greater than 0. Okay, so for that, for everyone, we are able to find probability density function, okay, and satisfy this equation, just like an ordinary PDF for some random variables. Okay, so this should be true for any intervals I. So under this assumption, we will have all of the stuff here we presented here. Okay. Now with this definition, we will go back to our purpose here. Okay. So we will check whether this definition gives us the identity here, right? Because originally, we want to find a proper definition of this object, right? At this point, we don't know how to define this conditional probability, okay, of event, given that the absolute continuous random variable x has a specific value little x. Okay. But with this assumption, and then we are able to give a definition of this conditional probability. Okay? In this way. All right? So we have to check that this definition is successful. How do we check that? We have to check that with this definition, then we can establish this identity. Right? This is because this is our goal. Okay. So now, for any Borel set A in R, we have okay. No? So with this definition, then we see that this implies that the probability of okay times is equal to okay. For all x n in R. Okay. So we have the identity. So this is good for all. Okay. So you can see that why this is true. Okay. we can consider two cases. First of all, when the PDF of x at x is positive, so when this is positive, okay, when this is positive, we have this by definition. So we move the denominator to there, we establish identity first, right? The second case is when this is 0, okay? When this is 0, and so that this is the okay, so when we know that when 0x and this is okay, by definition we know the PDF is the summation of all these conditional PDF, right? And it's 0, so this is implies that okay? So we know this is 0, right? And when probability of this event is 0, then this conditional probability by our definition is equal to this one. So that this implies that O1 to R. Okay? Why? Because when for n such that this probability is 0, this conditional PDF by definition is equal to f of x equal to x. But this is already 0, right? Okay? So this implies that this is true. Okay. So for this case, this is 0, and this is also 0, okay? This is also 0. Okay. All right, so we have 0 equal to 0, of course, right? 0 equal to 0, right? So the equality is true for all x n in R. Okay. All right, so that this is always true for all x n in R. So this is in. So we can replace this as is that okay? Because of the identity here. Because the identity. So we have this one, all right, and now this probability is independent of x. So this A. And by the remark we make here, the integration of the conditional PDF of x given n is just the conditional probability of the event that x in A okay. Okay, and so finally, this is equal to n equal to n and the x in A. Okay, okay, so we have achieved our goal, right? Because originally we asked for, when we give a proper definition of this one, then we have this identity, right? And by checking, we know that this is indeed the case. Okay, we have that. So that we can write down proposition 6.5.I. All right, so let n be a discrete random variable, and the x an absolutely continuous random variables with a PDF f sub f x. Okay. Right, so x itself n is a discrete random variable, and the x is an absolute continuous random variables. Then x is conditionally absolutely continuous given the discrete random variable n with conditional PDFs f of x given n for all n with probability that greater than or equal to 0. Okay? So this is our required condition, right? If and only if for each n with that probability of random variable n equal to n is positive, there exists, okay, an integrable non-negative function of x in R such that in R such that the probability of that n equal to n, but x in A is equal to the integration of this function weighted by the PDF of x for any Borel set A in R. Okay? Furthermore, we have that the probability this is equal to okay. for all n x in R, where fx is defined to be if So the required condition that x is continuous is conditionally absolutely continuous given the discrete random variable n. If and only if that we can establish a conditional probability, such a function. Okay, so for each n with this probability greater than 0, there exists an integrable and the integral function of x. Okay, such that we have this identity. Okay. Any questions? What? Okay, and the next section is about other statistics, but we will omit this section. But if you have time, you are encouraged to read this section, because this section contains very interesting and important results. Because in some engineering and mathematical problems, we need all the statistics. Okay, but but I will omit it. The last section, I mean, in my class lecture, the joint probability, we will consider the joint probability distribution of functions of random variables. Okay, so if we have a finite number of random variables, then they may go through different types of data processing functions. Okay, so we may have say m or n data processing functions, and get a new finite number of random variables. All right, so the problem is that if the original random variables are jointly absolutely continuous, then the question is, are these new random variables jointly absolutely continuous? If the answer is yes, how do we compute a joint probability density function for this new random variable from a joint PDF of all the random variables? Okay, so that is the problem. And as you can see, this is an extension of the last section in previous chapter, because in chapter 5, we consider the distribution of a function of a random variable when this random variable is absolutely continuous. Okay. Okay, so I just described a couple of definitions, and because the time limitation, then I will give you class notes on this section. Okay. A subset U in n-dimensional Euclidean space is called open if for every point x in U, there exists an open M-ball. An open M-ball is something like here. Consists of all points in Rn such that the distance from x is less than r. Okay, so the open M-ball with the center. So you can see the M-ball has the center x, right, and the radius r greater than 0, right, which is contained in U. Okay. So in R2, so this is an open set, because for any point x here, we can find an open disk, which is the open two-ball, okay? And the radius is r. Yeah. So this is B, here. And the whole, so this is U, contained in U. Okay. It's just like an open set in the real line. Okay. So a subset of the real line is an open set. If for each point we can find an open interval, okay, a very small open interval with center x, right? Such that the whole open interval is contained in the set. Okay. All right. So this is called the open ball. Now we let x1, x2 up to xn be jointly absolute continuous random variables. Okay? And we let now we let U be an open set in Rn which contains the range of the random vectors. We know a random vector is equal to n. Okay? It's defined on the sample space, and the value is an n vector in the n-dimensional Euclidean space. And we collect all the possible value, which is called the range. And we ask that U is an open set which contains the range, all right, of this random vector. Okay. Now consider n Borel measurable real valued function G sub I of G sub J of x1, x2 up to xn on U for all j from 1 to n. Okay? Right? So we are, suppose we have n random variable. They are jointly absolute continuous. And suppose we have n Borel measurable real value functions. Now, by proposition 6.1.c, that if we define y sub j as the data processed result, okay, all right, random variables too, okay? So we know they are variables too. So the question is, are y1, y2 up to yn jointly, absolutely continuous? All right, so the question is that, and if yes, how do we find a joint PDF for them? Okay. Okay, so we will develop, okay, several propositions to answer these questions, okay? And the idea will be the same as the idea we took in the last section of chapter 5, okay? All right, so please see the class lecture note, which will be distributed later. Okay. Okay. So we'll have the second midterm examination next Thursday, right? All right. So I stop here.